Hi, hello everyone. Welcome to my channel. Today, let us see about the brief introduction to atom. First, let us see what is an atom. Atom was discovered by John Dalton. He proposed the famous atomic theory in 1807. Atom is the fundamental building blocks of matter. Matter is anything that takes up space and has mass. The existence of different kinds of matter is due to different atoms consisting them. The atom has been derived from Greek word that is atomia, which means uncuttable or non-divisible. The structure of the atom is the center of the atom is nucleus, which contains of protons and neutrons. The electrons are revolving around the nucleus. This is the structure of the atom. It has a protons and neutrons at the center of the atom, and the electrons are revolving around the nucleus. And the atomic theory of matter was first proposed by John Dalton. We already know that he was a British school teacher in 1808. Dalton's atomic theory was able to explain law of conservation of mass, law of constant composition and law of multiple proportion very successfully. However, it failed to explain the results of many experiments. For example, it was known that substance like glass or ebonite, when rubbed with a silk or fur, it gets electrically charged. Those things were failed to explain. Now let us see about the discovery of the subatomic particles. In 1900, J.J. Thomson discovered the presence of the negatively charged particles called electrons in the atom. He was the first person who discovered the electrons which is present in the atom. E. Goldstein discovered new radiations in gas discharge and called them Kinol rays. These rays were positively charged. This later led to the discovery of the positively charged particles called protons in the atom. It was identified and named by Ernest Rutherford. His period was 1917 to 1920. In 1932, Chadwick discovered the presence of particles having no charge in the atom and he called as neutrons. Then let us say about the discovery of the electron. In the late 19th century, physicist J.J. Thomson began experimenting with cathode ray tubes. Cathode ray tubes are sealed glass tubes from which most of the air has been evacuated. A high voltage is applied across two electrodes at one end of the tube, which causes a beam of particles to flow from the cathode, that is the negatively charged electrode, to the anode, which is the positively charged electrode. The tubes are called cathode ray tubes because the particle beam or cathode ray originates at the cathode, so then it was called as a cathode ray tube. The ray can be detected by painting a material known as phosphors onto the far end of the tube beyond the anode. The phosphor spark or emit light when impacted by the cathode ray. To test the properties of the particles, Thomson placed two oppositely charged electric plates around the cathode ray. The cathode ray was deflected away from the negatively charged electric plate and towards the positively charged plate. This indicated that the cathode ray was composed of negatively charged particles. Thomson also placed two magnets on either side of the tube and observed that this magnetic field also deflected the cathode ray. The results of these experiments helped Thomson to determine the mass to charge ratio of the cathode ray particles, which led to the fascinating discovering the mass of each particle was much smaller than that of any known atom. We can see the cathode and the anode which is present in the either side of the cathode ray tube, and when the high voltage is applied, some of the particles which gets emit from the cathode electrode to the anode. From this experiment, he discovered the electron. He discovered the electron. That is, electron is a negatively charged thing which always tends to move towards the positive thing. So, cathode is a negative electrode. From the negative electrode, the electron is produced which moves towards the positively charged electrode. From this experiment, he concluded that the ray, that is a particle which emits from the cathode, is a electron. Now let us see about the discovery of the proton. In 1909, Rutherford discovered proton in his famous gold foil experiment. What is the gold foil experiment? Let us see about that. In his gold foil experiment, Rutherford bombarded a beam of alpha particles on an ultra thin gold foil and then detected the scattered alpha particles in zinc sulfate screen. The results was most of the particles passed through the foil without any deflection. Some of the alpha particles deflect at small angle, very few bounce back, that is 1 in 20,000. Of the Rutherford's experiment, from the alpha particle emitter, Alpha particles are emitted and that is falling on the gold foil. The alpha particles are passes through the gold foil without any deflection. Most of the particles are just passing through the gold foil, and only few of the particles gets deflected. Conclusion of this experiment. Based on his observations, Rutherford proposed the following structural features of an atom. Most of the atom's mass and its entire positive charge are confined in a small core called nucleus. The positively charged particle is called proton. Most of the volume of an atom is empty space. How he concluded that most of the atom is empty space? Only because of the empty space only the particles are non-deflected. If some obstacles or some particles are present in somewhere, means it when it strike on the particle it gets deflected, but here mostly all the particles are non-deflected. From that he concluded that most of the volume of an atom is the number of negatively charged electrons dispersed outside the nucleus is same as number of positively charged in the nucleus. It explains the overall electrical neutrality of an atom. Then discovery of the neutrons. Various experiments were conducted and several theories and observations resulted in the discovery of neutrons. Few noteworthy experiments and the observations are listed below. And H. Baker, while bombarding beryllium with alpha particles, observed electrically neutral radiation in the year 1930. The scientists believed it to be photons with high energies, also known as gamma rays. In the year 1932, Ernie and Frederick Joliot Curie demonstrated that this ray has the potential to eject protons when it strikes paraffin or any H-containing compounds. This, however, raised many questions such as how a photon that does not have mass can release a particle that is 1836 times heavier than an electron or proton. Therefore, it was concluded that the ejected rays cannot be photons. In the year 1932, James Chadwick conducted the same experiment, but he used different bombardment targets other than paraffin. After research and analysis of the various targets, he discovered the presence of the new particle. This new particle has this mass similar to that of the proton but no charge. He named these particles neutrons. Furthermore, he derived the nearly accurate mass of this new particle by applying the conservation of energy and momentum. He measured the mass of a neutron to be nearly same as that of a proton. This is the mass of the proton. Function of neutrons. James Chadwick concluded the nucleus consists of proton and neutron. Together, these two subatomic particles are termed as nuclei. The discovery helped to understand the atomic mass and the atomic number more clearly. It also helped in understanding the concept of isotopes, which forms the basis of radioactivity. Beryllium reaction, when it is bombarded with the alpha particles, it comes like this. Then chemical symbol of a particular element should be represented as Ab, calcium, sodium, whatever. So the symbol of the particular element is represented by X and the neutron number is N, then atomic number as Z, then mass number is A. Atomic number is nothing but number of protons and mass number is nothing but number of protons plus number of neutron is equal to mass number. After the discovery of the neutron, every chemical element present in the periodic table was modified and written accordingly. For instance, uranium was written as U-23592. This means that a single atom of uranium contains 235 nucleons, that is, protons plus neutrons. Mass number. So usually mass number should be right in the top of that element. Out of 235 nucleons, 92 are protons and 143 are neutrons. Now let us see about the atomic models. So Dalton model, it is also called the billiard ball model. In Thomson model, it is called as plum pudding model. Lewis model is cubical atom model. Nagoka model is a Saturnian model. Rutherford model, planetary model, Bohr-Sommerfeld model, and Grenzky model. So many models are there. We will see a few models. First one is a Thomson model of an atom. J. Thomson in 1898 proposed that an atom possesses a spherical shape, that is, a radius is approximately 10 to 10 meter, in which the positively charged is uniformly distributed. The electrons are embedded into it in such a manner as to give the most statical electrostatic arrangement. This image represents the Thomson atomic model. He compared that atom with the watermelon. Here in watermelon, we can able to see the red color portion. He compared the atom's proton with the red color portion, and the negative, that is a negative charge, is electron is there, no? So he compared the electron with the seeds of the watermelon, which is embedded in the fleshy part. So many different names are given to this model. For example, plum pudding, raisin pudding, or watermelon model. An important feature of this model is that the mass of the atom is uniformly distributed over the atom. Although this model was able to explain the overall utility of the atom, but was not consistent with the results of later experiment. Thomson was awarded Nobel Prize for Physics in 1906 for his theoretical and experimental investigations of electricity by gases. Next, let us see about the Rutherford's nuclear model of atom. Rutherford and his students named Hans Jaeger and Ernest Marsden bombarded very thin gold foil with alpha particles. A stream of high energy alpha particles from a radioactive source was directed at a thin foil of a gold metal. The thin foil had a circular fluorescent zinc sulfate screen around it. Whenever alpha particles struck the screen, a tiny flash of light was produced at the point. The results of this experiment were unexpected. It was observed most of the alpha particles passed through the gold foil undeflected. A small fraction of alpha particles was deflected by small angles. A very few particles, 1 in 20,000 bounced back, that is, were deflected by nearly 180 degree. On the basis of the observation, Rutherford drew the following conclusion. First one is, most of the space in the atom is empty as most of the alpha particles passed through the foil undeflected. A few positively charged alpha particles were deflected. The deflection must be due to enormous repulsive force, showing the positive charge of the atom is not spread throughout the atom as Thomson has presumed. The positive charge has to be concentrated in a very small volume that repelled and deflected the positive charged alpha particles. Calculations by Rutherford show that the volume occupied by the nucleus is negligibly small as compared to the total volume of the atom. One can appreciate this difference in size by realizing that if a cricket ball represents its nucleus, then the radius of atom would be about 5 km. Conclusions: the positive charge and the most of the mass of the atom was densely concentrated in an extremely small region. This concentrated region was called nucleus by the Rutherford. The nucleus was surrounded by electrons moving in a very high speed in circular paths called orbits. Thus, Rutherford's model of atom resembles the solar system, in which nucleus plays the role of the sun and the electrons that of revolving planets. Electrons in the nucleus are held together by electrostatic force of attraction. The drawbacks of Rutherford's model of an atom: it could not explain the gravitational force in nature, then planetary motion under the influence of gravity, Maxwell's electromagnetic radiation property. Then it also cannot explain the stability of an atom. Then it could not explain the distribution of electrons around the nucleus and the energies of these electrons. It could not explain quantum mechanics as a whole also. Now let us see about the Bohr's atomic model. A Danish physicist named Niels Bohr in 1913 proposed the Bohr atomic model. He modified the problems and limitations associated with Rutherford's model of an atom. Earlier, in Rutherford's model, Rutherford explained in an atom a nucleus is positively charged and is surrounded by electrons, that is a negatively charged particle. According to Bohr atomic model, a small positively charged nucleus is surrounded by revolving negatively charged electrons in fixed orbits. He concluded that electron will have more energy if it is located away from the nucleus, whereas the electrons will have less energy if it is located near the nucleus. Here in this diagram, we can able to see different orbits are there, right? Different levels are there. So first one is the 1, 2, 3. We can call it as also K, L, M, etc. That is, the electron travels in circular orbits around the nucleus. The orbits have quantized size and energies. Energy is emitted from the atom when the electron jumps from one orbit to another close to the nucleus. Shown here is the first Balmer transition. That is, what is happening is, in which an electron jumps from orbit third N3, that is a M level right now, to orbit N2, producing a photon of red light with an energy of something. Then postulates of the Bohr atomic model. The electrons revolve around the nucleus in a fixed circular path termed orbits or shells or energy level. The orbits are termed as stationary orbit. Every circular orbit will have a certain amount of fixed energy, and these circular orbits were termed orbital shells. The electrons will not radiate energy as long as they continue to revolve around the nucleus in the fixed orbital shells. The different energy levels are denoted by integers such as 1, 2, 3 and so on. These are called as the quantum numbers. The range of quantum number may vary and begin from the lowest energy level, that is a 1, to the highest energy level. The different energy levels or orbits are represented in two ways. It may be a 1, 2, 3 or k element. The lowest energy level of the electron is called as the ground state. The change in energy occurs when the electron jump from one energy level to other. Atom, the electrons move from lower to higher energy level by acquiring the required energy. However, when an electron loses energy, it moves from higher to lower energy level. Therefore, the maximum number is given by the formula 2n power 2, where n is the serial number of the cell. The maximum number of the electrons in K, L, M, N, O, P, Q are 2, 8, 18, 32, 50, 72, 90 exactly. For the first cell, only 2 electrons can accommodate. For the first cell, there is a K shell, only 2 electrons can accommodate. The shells are subdivided into subcells, that is, the number of subcells in a shell is equal to the number of the shell from within. K shell has one subshell and it is called as S. For L, there is two subshells, that is S and P. For M, 3, there is a S, P and D. For an N shell, there is a 4 subshells, that is S, P, D and F. The subshells S, P, D and F can have a maximum of 2, 6, 10 and 14 electrons respectively. Finally, let us see about the valency. What is meant by valency? So, valency is the combining capacity of an atom of an element. The electrons present in the outermost shell of an atom are called valence electrons. Outermost shell is completely filled, they are inert or least reactive, and their combining capacity or valency is 0. Of the inert elements, helium atom has 2 electrons in the outermost shell, and the atoms of other elements have 8 electrons in their outermost shell. Atoms having 8 electrons in their outermost shell is having octet configuration and are stable. If an atom's outermost shell is not completely filled, it is not stable. It will try to attain stability by losing, gaining or sharing electrons with other atoms to attain octet configuration. The number of electrons lost, gained or shared by an atom to attain octet configuration is the combining capacity or the valency of the element. For example, for the hydrogen, lithium, sodium like elements, it can easily lose one electron and become stable, so their valency is 1. For the magnesium, it can have the capacity to lose 2 electrons easily, so its valency is 2. For the aluminium, 3 electrons, so its valency is 3. Carbon, it can share 4 electrons, so its valency is 4. We can say valency not only in the loss but also in the gain. The rest can easily gain 1 electron and become stable, so its valency is 1. Oxygen has the capacity to get or gain 2 electrons from nearby element or atom, so its valency is 2. Nitrogen can easily gain 3 electrons, so its valency is 3. Thank you for listening.